Very good evening to you all. Today we are back at Let's Code MS-DOS, and this time we are looking at another demo effect from the PC demo scene. Well, actually, I think this was done on other platforms as well, maybe on the Amiga. I definitely saw this on the Amiga as well, but I'm not sure if it was the same time frame. But I am mainly talking about one demo that changed basically the whole PC demo landscape, and that is Second Reality by the Future Crew. I think that demo was released in 1993, might have been 1992, but I think it was 93, and it was different. There were so many parts in there, it was truly a mega demo, and there were effects that haven't been seen before, or haven't been seen before in that quality and that smoothness, etc. So one thing that fascinated me as a kid when I saw this was the part with the Rotozoomer. I will put it on screen now, and there is this nice pixel image of this weird demonic guy, and a spherical ball is bumping up and down, and once it leaves there is this very famous sample being played, and suddenly the whole screen starts to zoom and rotate, and I was thinking, wow, how is that possible? What kind of stuff do you need to know to do this actually? And it took me a very long time to understand what is actually happening there. You actually need some linear algebra for that, and I will show you the rough basic ideas behind that in a minute. And the problem is, those old PCs, this was running like on a 486, 33 megahertz or something, and very smoothly indeed. They didn't have a lot of processing power. They could do integer arithmetics very well, floating point not so much. So pure 3D was very hard, especially with textures. This is also some kind of texture mapping, but it's only 2D, so you can leave out quite a few of costly computations. And first of all, we probably should talk about the texturing problem. So let's first do that, and we'll look at the bench, and I'll draw something up, and then we'll come back to this. So let's talk about texturing, or what is behind the maths of the Rotozoomer. So texturing means applying one image to a different image basically, and transforming the source image in the process. We have our source image, which is the demonic guy somehow, and we will parameterize this thing not with x and y coordinates, but we will call those coordinates u and v. And we will also have our screen, which is parameterized with x coordinates and y coordinates as we know them. Usually the screen will have a certain resolution, for example 320 by 200 for the VGA card in our usual modes, but could be anything. The source image similarly will have any size. I think I scaled it down to 128 by 128, I think, but you can check that later. And it will be, in our case, a square image of some demonic guy. Well, I'll be drawing a smiley here because it's easier to draw. So the question is now, how can we apply this texture source to the screen and rotate and scale it? Well, to rotate and scale it, and maybe even translate it, we will have to put it somewhere here on the screen. Let's say we want to rotate it like this, and also scale it like this, and then of course it will get tiled over the whole image, as you can imagine. But we are actually more interested in how we do the first step, because the following steps will just be repeating this over and over again. So we have the u coordinates here, which will be mapped to this arrow over here. We can already see that there will be an angle of rotation in this direction, and we call this angle theta. And doing such a rotation of some vector, some point in 2D is actually rather simple. We can write down a rotation matrix, and if you don't know matrices and vectors, you should look it up, but the important thing is a point on a plane or a vector, so a direction on a plane, can always be described by two components, x and y for example, and we write them like this in a column. Furthermore, if we want to transform such a two-dimensional vector, we will have a matrix. A matrix is basically a table, like an Excel sheet or something, and there will be values in here that define how the vector is transformed, some numbers basically. And if we multiply this transformation matrix by this vector, we get a new vector which is transformed. And that new vector will be this component times this component plus this component times this component in the x component. And in the y component we get this component times this plus this component times this. So what does the rotation matrix look like? The rotation matrix actually looks like this. We take the cosine of this theta angle, and we take the negative sine of the theta, and we also take the sine of the theta and the cosine of the theta again. And when we multiply this, we get x times cosine of theta minus y times sine of theta in the x component. And the second component of this vector is x times sine of theta plus y times cosine of theta. So this is no longer a matrix, but a vector with this stuff in here. So we just have to write these two formula into our code and multiply every pixel coordinate basically that we have on the screen. Plug that into there, and then we get basically our UV coordinates here. And we can use that to look up in the texture. Furthermore, we can also apply some kind of scaling on top of that. That means we can also write some scaling factor here to get the zoom into there and ramp that up and down. And we can also translate everything, which means we can have our UV coordinates, but add an additional vector, which we call t. And this will have a tx and a ty component for shifting along the x or y axis, for example. Or we could also call it tu and tv because we are shifting in texture space. But it doesn't matter where you shift so long as you do it. And that is more or less it. The whole magic is basically just this rotation matrix and how to implement this efficiently to get the screen going here. We will now have a look at the code and see how we can map this whole stuff that we saw here into TurboC. We should look at the code. I have prepared a skeleton program which is based on our other demo effect programs, and it looks very, very similar. One thing has made a comeback, namely the GIF header, because we want to load an image, and I actually prepared the original Future Crew image in some fashion, so we will be able to replicate this process more or less like it was in the actual demo. Then we also have a bunch of sine tables and the palette for the GIF and the image structure for the GIF. If you're not familiar with this, I will link to the episodes which talk about sine tables and the GIF loading in the upper corner, I hope. I hope I don't forget that, and then you can look that up first. The initialization of the sign tables I will skip, but I will talk a little bit for a short while about the main function, which is very similar to the other demo effects that we did. Mainly we allocate a frame buffer, we load the GIF image, and then I have prepared two different versions of the algorithm. For the fire and plasma effects we already used the mode Y with its capability of drawing 4 pixels at once with the same color to get a very blocky but very fast effect. We will do this here as well for speed purposes, but also it might be too blocky because we actually want to see something here. So I have an alternative code path here which uses just the regular mode, what do we use? No, the mode 13, and simply copies the whole frame buffer from memory to the VGA. We are rendering just like Future Crew did with 160 by 100 pixels. Don't be fooled by the 320 here, because the program will actually draw 2 pixels at once. So it has 160 by 100 resolution, and we double every scan line basically in this memcopy loop. This will give us a relatively fast solution. One thing where the Future Crew is much faster at is because they use better tools. I'm doing this in TurboC 2.0 because to show that you can do it. You can code it in 16-bit, it will be slow. The Future Crew used 32-bit opcodes, probably a bit of assembly language, I don't know. You can look up the source code of the effect in the source code of Second Reality. So we will definitely be much slower because this is not very optimized and the TurboC compiler will not optimize very well. But it shows that it can be done on a 16-bit processor. It would even run on a 286, probably terribly slow, but it would work, and that's the nice thing, I think. And yeah, recoding this in assembly language with 386 opcodes and 32-bit data path will be much faster, of course. But then we probably will be here for a couple of episodes. So that's not the scope of today. So the main routine will be just this: draw roto. It takes the usual parameters, an x and y coordinate where to start the effect, and a width and height. So you can basically scale it up and down and position it on the screen just as usual, and a time index t to animate the whole thing. I will actually code 2 versions of this. I will do one with floating point because it's easier to read, and then we will do one with fixed point integer arithmetic because it will be actually much faster on a real PC. On this DOS box it will probably be similar because my Core i5 here has a very powerful FPU and it can do the FPU stuff very fast, so it doesn't matter, I guess. But if you put it on a real PC, having the integer operations will probably be much better, much faster. Alright, so let's get started. I will actually already use the constant that I defined up here, if-def useFloat, and there will be an else path for the fixed integer arithmetics, which we will fill in later, maybe even a second episode. I'm not sure yet how long this will take. And there is this define up here useFloat, which will choose this code path, so we get the floating point operations, and then you can swap around between both parts by just undefining that simple toggle switch basically, and recompile the program, and you have the integer version. Okay, so first of all we need some kind of angle, and we will define everything const so that the compiler knows, okay, this is not a variable, it's constant, I can put it in a register or just use whatever optimizations. Not sure how well TurboC honors that, but we can give it a hint. So the angle that we are rotating the image by, the theta, I think we called it in our sketch just a minute ago, is pi times our current time index divided by 180. converting from degrees to radians because we need to feed that into the sine and cosine functions actually. Which leads us to the next. As we've seen for the rotation matrix, we need both the the cosine and the sine, and we will also store this because it will be used multiple times and we need to compute it only once, and the computation is expensive obviously. Which is why we have the sine tables for the fixed integer part, but that's for later. So we store the cosine and we also store the sine of the angle. And at some point we also want to have a zoom, and we call this Z. And this will also be like a sine, so I take the sine value that we just computed, and because I don't want to make it negative, I actually add 1.5, so we never get a zoom factor of 0, which would make every pixel infinitely large, and we get a certain minimum amount of zoom. But you can play around with these values. It makes for some interesting effects. Going negative might actually flip around the image, etc. Yeah. And also we wanted to translate our rotated image. So we have a translate vector, which is tx and also ty. This is the translation part. And for that we also take some sine function, but we add some, or we multiply it by some constant. I took 64, you can choose whatever you like. And I also make it so that it never goes below 0, but you can play around with those. And I use the cosine for the y part, because if you plot the sine against the cosine, you get actually circles, so we get some kind of rotational movement. That's at least the idea. Again, you can use basically any function here. You could even use a linear function or just leave it out, then you won't get any translation part. But yeah, that's okay. Furthermore, we need a couple of variables. I will call them JS and JC because they are the product of our current loop. We will have two loops, one over I, one over j, for the actual u and v coordinates later. And one will be the product of that variable with sine and with cosine. And for the inner part, for the inner loop, we will have something similar. We will have something called ICJS, which is the product of I with C plus the product of j with S. And the same goes for ISJC. Once we wrote that down, you will see the similarities to the rotation matrix that we talked about earlier. This is basically the vector multiplied with the rotation matrix. And so, first of all, we can initialize JS and we can initialize also JC. So this, so that we don't have to evaluate it completely every time, but can use a simple addition to update this variable, because multiplications and divisions are always expensive, both with floating points as well as with integers, and additions are much faster. So we initialize this with our start coordinate, which is y plus ty actually, because that's the translation, times the sine. So that's the first part. And the other part is the cosine product. And as you can see, the outer loop will be over the y coordinate, obviously. So that's what we write down. We write down the loop. The loop goes like this. J is equal to 0. Also, for the pixel setting purposes, we won't be computing the pixel coordinate all the time. So we will also carry a pointer to the pixel, which we need to introduce here. So this is a far pointer to the pixel, which will point just into the VGA memory. And we initialize that with the first pixel. which actually is our frame buffer pointer, plus of course our start coordinates, which is y times width plus x. So this is the very first pixel that we want to write to. This is similar to what we always do. And for readability, I'm gonna make a line break here. The end will be reached when j has reached h, so the height of the image. It goes from 0 to the height of the image. Okay, and in every loop we need to update something. And we need to update our j, obviously. We just incremented. And we need to update our pointer to the pixel. So how much do we need to add? Well, we need to skip to the next line, which is screen width, minus the width, actually, of the image that we are writing. And that's it for the outer loop, actually, at least for the header. But what do we do inside? Well, inside we do something very similar. We initialize the variables for the inner loop. And that was the ICJS, which is something, and the ISJC, which is something. And that will obviously be something to do with JS and JC, which we initialized up here. And we have something very similar for the x-coordinate, obviously. So we take the x-coordinate plus the translation, and we'll animate, we will rotate that, and our rotation matrix tells us that this should be the c, the cosine, and we have to subtract the sine part. You remember, it's basically x part times c minus y part times the sine. And for the second part, it's very similar. We have, let me think, the very same. X plus tx is our x-coordinate that we want to transform, times the sine, and this time it's plus the cosine part. Okay, so all these lines together basically give us our evaluated rotation matrix. That's more or less already the whole magic. The rest of the function will be just updating the variables in the correct fashion. So first of all, we need to loop again. And this time it's the I variable that I picked. Do I need to carry anything else? No. This time it's only the I variable because the pixels are tracked in the outer part, basically. Or almost. Yes. The end condition is when I reaches the width of the image, and we increment I. Alright. Opening and closing the loop. Now we can actually compute the u and v coordinates, which are the actual texture space coordinates. The u will be something like this. We'll take the transform coordinate and apply the zoom factor to it, which will make the image larger or smaller. But we can't use that because this is a floating point variable. So we basically just cast the whole thing to an 16-bit integer, because this is our lookup into the texture. And we have to make this the size of the texture image that we're actually using. So image width. So that whenever this gets larger, we wrap around to the left side, so we get this nice tiling pattern. The same goes for the v coordinate. It's very similar, but this time we have ISJC. And it's not the width, but the height, if they are different from each other. If it's not a square image. Then we need to fetch the color. So we take a, I need to introduce a color, I think, up here. Byte col. So color is our macro get image, which you can look up above, and then just the u and v coordinates. This will take the sample. And now we come to the magic. we need to write that. So the pixel pointer will be dereferenced. That means we will write to it, and after that we will go to the next pixel, plus plus, which is fine. Which is also why we do the minus width here, because we will write width number of pixels. So we need to skip ahead, screen width minus width. So pixel plus plus equals color. And now comes the magic with the mode Y. If we are not in mode Y, where we basically write 4 pixels at once, we need to write a second pixel to make it fast enough. So we will do the same again in that case. If you don't understand it right now, you can play around with the code and see what happens when you take it out. You will see that there will be black spots in the image. So yeah, just play with the code then. And of course, we will also have to increment I once more, which is fine, because we already wrote another pixel. And the true magic is now how we update the matrix variables. So IC.js, we could have computed that all the time, basically with multiplications, but it's expensive. But since we already initialized it in such a nice fashion, the next multiplication would just lead an increment of exactly the cosine that we computed. Because every time you increment the I, basically, you're just incrementing the whole thing by the cosine, because it's I times c, and first it's 1 times c, then it's 2 times c. So instead we can just add the cosine every time, instead of recomputing the whole product every time, which is much more expensive. And the same goes, of course, for the other variable. ISJC equals plus equals the sign. It's just the same thing. It's I times s, so 1 times s, 2 times s, 3 times s. So every time you just add an s. It's the very same thing. Same goes for JS and JC. Outside of this I loop and inside of the J loop, we can increment JS by just adding another s. And JC will be incremented by c. So, what else is there that we need to do? Well, actually, this is the whole thing. With floating points, obviously. We will try to compile this and see if it works. It might not work, I might have mistyped as usual. And there are a couple of errors because I forgot, of course, some run variables for the loop. Let me see, what did I forget? Okay, yeah, we want something like word ij, and I think UV is missing. That was an in16t, which is actually the same now as the word, but yeah, whatever, it will suit. And that looks good. Let us see if it works or if we coded some garbage. Hey, look at that. That is, I think, already pretty impressive. It's a bit slow. I will increase the cycle count to make it a bit more watchable. Yeah, no, this is looking good, I think. This is the 160 by 100 resolution with floating point variables, which will run horribly slow on the 486, and we will talk about how to make this faster, but for now we can already gaze upon this very cool effect, I think. Since we are already at 30 minutes in this video, I will cut this short and show you the fixed point computations in the next video. But for now, thank you very much. Please consider subscribing, liking and sharing the video. And as usual, if you want to support me, you can do this via PayPal, Patreon or Ko-Fi. Links are in the video description. If you don't, that's also fine. Give your support to any creator that you like. Definitely leave a comment. Let's discuss this thing and what your thoughts are about second reality, or if you have ever heard about it, which I hope you do. If not, check it out. There are YouTube captures of the video, of the demo, let's say. And yeah, so far I'd like to wish you a very pleasant evening and see you next time.